It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on in-situ testing in geotechnical engineering, which will be delivered by Professor Emeritus Peter K. Robertson and Engineer Diego Marchetti. Engineer Diego Marchetti worked since 2001 in association with Professor Silvano Marchetti, the original inventor of the flat plate dilatometer, DMT, in 1980, used in over 80 countries worldwide. Together they developed and patented the Seismic Dilatometer, SDMT, in 2004 and the fully automated dilatometer, Modulus DMT, completed in 2019 and employed today in 4 continents. In 2009 they founded Studio Professor Marchetti, the company where Diego became director in 2016, after Silvano passed away. The main activities of the company consist in the design, production and distribution of patented geotechnical and geophysical equipment for in-situ testing. In particularly challenging surveys, such as offshore DMT and SDMT surveys, Diego provides coordination and assistance on site for ensuring high-quality testing with the supplied equipment. His research activities are mainly in cooperation with the University of L'Aquila and also with other worldwide universities and institutes. He is co-author of over 70 publications in technical journals and conference proceedings. Diego was invited and delivered technical presentations in over 60 countries at national and international conferences and to universities, research institutes and private companies.
Good morning or good afternoon, according to where you are in the world. I'm honored to deliver this lecture, and I will try to introduce you the flat dilatometer and seismic dilatometer from different points of views, and make it, I hope, interesting both for technicians, geotechnical engineers, and whoever is trying to participate. So, of course, in 50 minutes time, I can do a brief introduction and not go into all the details, but I will give you references for additional information and my contact in case you have additional questions beyond the questions and answers session after this presentation. So the flat dilatometer was invented by Professor Silvano Marchetti in 1974. He was in the big environment of the geotechnical professors like Professor Schmertman, Mike Malkowski, Roger Frank, and you may see a lot of other other people in this. That was the last DMT conference, International DMT conference in 2015, held in Rome, and then in 2016 he passed away. So we have to thank this man for the existence of the flat dilatometer. In the last years, there has been a strong migration in penetrable soils from laboratory testing to direct push technology. Direct push technology is composed of seismic CPT or CPT and DMT or seismic DMT. The reason is that direct push technology is simple, is fast, provides repeatable results, continuous soil profiles, and the results are available real time. Furthermore, in sands, recovering undisturbed samples is very difficult, so direct push technology is the state of practice. Now, you have seen with Professor Robertson the CPT and perhaps the seismic CPT. In this presentation, we will talk about the DMT and the seismic DMT. The DMT or flat dilatometer is represented in the top part of this picture, of this slide, and in the lower part you see the seismic module that was added in 2004 in combination or even without a DMT, independently from the DMT. And so we will see both of these equipments in the next slides. Let's start with the dilatometer. The dilatometer is a stainless steel blade with a flexible membrane mounted on one of its sides. The test consists in advancing the blade using push rods, generally penetration rods, a pneumatic electric cable going from a control unit at surface into the push rods down to the blade, a penetration machine represented by the black arrow that we will see in the next slides, a control unit, and a gas tank of air or nitrogen for powering the pressure. A computer may be used to obtain automatic data acquisition and view the results real time, or also you can write the pressure readings on a notebook if you want to not have a computer on site, and then write the results on the computer in case you're in a harsh environment where computer is difficult to use. Now, the test procedure consists in advancing the blade in the soil and stopping every 20 centimeters to perform the following measurements: A, B, and C. Now, when the blade is advanced and stopped, initially the soil will flatten the membrane against the blade. The operator starts to inflate the gas, and when the membrane starts to expand or lift off, the A pressure reading is obtained. The operator continues to inflate the gas, the membrane continues to expand, and when it has expanded exactly 1.1 millimeter in its center, the second pressure reading B is obtained. Then the operator has to deflate the gas and the pressure. If not, the membrane will overinflate, and the membrane will return to the normal A position, which is called C when it's deflating. So the C is basically the opposite of the A reading. To see it to look into this mechanism, let me repeat it with this slide. So we push the blade into the soil. The pressure of the soil, which are the red arrows, flatten the membrane against what is behind it, and the contact of the membrane is on. Now the operator inflates, and when the pressure of the gas is in equilibrium with the pressure of the soil, the membrane starts to expand, and the signal of the contact membrane goes off. The operator continues to inflate. When the membrane has expanded 1.1 millimeter in the center, the contact goes back on and the B reading is obtained. Then you deflate, and when the contact goes back on, the C reading is obtained. So basically, a DMT test consists in taking every 20 centimeters 2 pressure readings, A and B, and eventually the C reading from time to time. We will see the meaning of these readings in the next slides. For what concerns the seismic equipment, it is composed of an instrumented rod that may be mounted behind the blade with the top and the lower sensor and an electronics, digital electronics inside this rod. Shear wave is generated at surface with an adequate shear beam and hammer, and with a configuration that is explained very much in detail during the training on the equipment. And when the hammer hits the plate, the shear wave will travel at depth and arrive to the top and to the bottom sensor. The electronics amplifies and digitizes the signal at depth, and the delay is evaluated automatically by the computer at surface, obtaining delta t, whereas the geometry determines the travel path of the wave from the center of the shear beam to the lower sensor and to the top sensor. So S2 minus S1 divided by the delay delta t in the arrival of the wave represents the average shear wave velocity between the two sensors, which are spaced ½ meter. If we have the shear wave velocity, thanks to the mass density and this well-known formula, we obtain the maximum shear modulus G0. Just to show you how simple it is, this is the interface of the acquisition where the default parameters are already set. You know the depth of the tip. You start with acquisition button, give a hammer blow to generate the shear wave, and in a matter of seconds, we see the recorded signals at surface with an average quality, which is the one that you see here, where the delay is very well defined and consistent. And the graph is also shown with the red seismogram rephased to the blue one to ensure that the delay was evaluated correctly and provide a real-time evaluation of the S. The measurement is generally repeated 2 or 3 times to ensure a good repeatability, and the variation coefficient is generally below 1–2%, but even below 5%, it is more than acceptable. Now, the main features of the system are that the text execution is very rapid, because no hole is necessary if the soil is penetrable. And if the soil is not penetrable, you can drill a hole, fill it with rounded gravel, and do the test inside. And you can read, there's a paper on this specific procedure. And you never have to wait for the cementation of the hole, like for a cross-hole or downhole, which can require several days. If the soil is penetrable, you take 30 meters, you can do them in about 3 hours. So it's very fast. The evaluation of the shear wave velocity is automatic. So often the post-processing is unnecessary. It's independent of the operator, provided that he configures correctly the position of the hammer and of the sensors. That is explained during the training of the equipment, and the results are obtained real time. The high quality of the delta T evaluation is mainly due to the following points. First of all, the quality of the electronics, which is custom designed for the automatic acquisition system. The signals are amplified and digitized at depth, so the signal cannot be corrupted compared to analog signals going at surface. And the more it goes deep, the more there is a silence from noise. So this allows clear waves and a delta T that is very consistent with a high accuracy in the evaluation of the S. The third important point is the true interval configuration, meaning that you use 2 sensors instead of using only 1. If you have only 1 sensor, you have to give a first hammer blow to give and record the signal. Then you have to go down at a fixed distance, for example, 0.5 meter or 1 meter. And if you make a small mistake in this depth difference, even very small, you can have a considerable error in the VS evaluation. Then you have to give a different hammer blow when the sensor, the only sensor of the pseudo-interval system is at the second depth. And this hammer blow is very difficult to give exactly in the same way, in the same direction, with the same energy of the first hammer blow. The offset of the trigger also may be different or slightly different between the first hammer blow and the second. There is no way that the pseudo-interval mono receiver can even get close to the accuracy of a true interval system, where the sensors are spaced at a fixed difference and the weight is the same and the trigger time is the same traveling to both sensors. So my recommendation is to consider only 2 receiver systems that are on the market besides this system, but never 1 receiver, which is definitely poor practice. The SDMT is considered quite a simple system, so many clients have asked to combine the SDMT with the CPT, and the SDMT cone is this combination of a CPT from many possible constructors. At the moment, Goda Geo, GeoMill, and Pagani support this combination, but virtually there's no limit with any other system. Now let's look at the penetration machines for advancing this testing equipment. Now the most productive way is to use a heavy truck penetrometer, which is able to advance the blade and the seismic DMT without lateral instability and pushing up to 20 or even 25 tons. Another alternative, more economical but very common, is to use a light penetrometer, which is able to push and sometimes even dynamically advance the system at depth. However, when it tries to push, it may arrive at a push force that is higher than the weight of the machine, and also the system of the pushing is not in the center of the machine, so it easily lifts when it's pushing. However, there is an anchoring system that enables to get the reaction force from the soil, and when the anchors work well, this machine can push at a good amount, up to 8–10 tons or even 12 sometimes. There are several other machines that may be employed to advance the DMT and the SDMT. Even dynamically, although it is not recommended, especially in soft soil, where the disturbance may be too high compared to the value of the soil. But in very consistent soil, the blade can be advanced with dynamic hammer blows, or very commonly pushed by a drill rig, or with the alternation of driving and pushing with a light penetrometer, or any other system you can think of, because the blade performs measurements not during penetration like the CPT, but when it is at depth, and how it arrived at that depth is not important. This is a detail of when using a drill rig and using the torpedo method. Like the SPT, there is a drilled borehole. The torpedo is assembled at the beginning of the test, once for all, with the blade, the lower adapter, and 3 or 5 meter long rods, and a top adapter connecting to the drill rods and allowing for the exit of the cable, so that the cable passes in the penetration rods and out of the drill rods to the acquisition system. And you can alternate the drilling, and when you finish the drilling, you lower this system connected to the drill rods and with the cable taped to the drill rods, lower it to the bottom of the borehole and push every 20 centimeters to do the test. Of course, this method is slower than a normal penetrometer. However, it has the big advantage that if there is an obstacle, you can drill through it and continue below. The tests, the DMT and also the SDMT, can be performed also offshore. It has been performed in lakes, rivers, sea. This is in the lake in the north of Italy, where we had 50 meters of water and 12 meters of penetration in this case. We lowered also a seafloor hammer, and it is possible, and it was very successful. We don't have time to look into all the offshore possibilities. However, there are papers published on this, and even a presentation that I can forward you if you're interested. The DMT is employable in all penetrable sands, silts, and clays, where the grains are small compared to the membrane dimensions. This means from very, very soft soils up to very hard and consistent soils, almost a soft rock with very high values of drain shear strength and modulus M. The blade is very robust and may withstand a push force of up to 25 tons. Generally, the limitation is not the blade, but the rods, which break easier than the blade itself. The SDMT is also employable in all penetrable sands, silts, and clays, but it can be employed also in non-penetrable soils like gravel or very dense sand, in a backfilled borehole, as I previously stated, with rounded gravel, and then using a top-down procedure or a bottom-up procedure. Some information may be found in this publication, or I can share some additional information on this methodology. And this is how we reached 135 meters with seismic equipment in the town of L'Aquila after the earthquake of 2009. Now let's look at the interpretation of the results. We said that we come back from the office for the DMT results with A, B, and eventually some C readings. What the first step of the interpretation is to correct the field readings with the membrane calibration, because the membrane is made of steel, so it has its own rigidity. And basically we do A and B readings in air and free air and obtained delta A and delta B. These values are then subtracted somehow from the field readings and depth, where it is soil plus membrane, and basically we have the net values of P0, P1, and P2, which correspond to the corrected A, corrected B, and corrected C reading, from gross to net, basically. The most important step is this step, from the corrected readings, P0, P1, and P2, to the intermediate parameters. Please consider that these parameters are not correlations, but definitions, and have a very specific meaning in terms of geotechnical and soil properties. ID, KD, ED, and UD, which we will see in depth in the next slides. Now, the final step is to use the intermediate parameters that are used like ingredients in the formula and in the correlations that Professor Marchetti found in 1980 to obtain the classical geotechnical parameters that are used every day in design and in geotechnical problems. So this is the list of the geotechnical parameters, and we will see them throughout also the next slides. This is the abacus of the formula. You see again the identification of the field readings, A, B, C, delta A, delta B, and the dissipation readings. I will talk about the dissipation test later on. And then the corrected readings, P0, P1, and P2, the intermediate parameters that we just saw, ID, KD, UD, and the flex point for the dissipation test, and then the interpreted geotechnical parameters, which come from the correlations obtained in many research test sites in the world that Professor Marchetti visited in 20, 30 years of his career, and which are the best way to estimate these parameters from the DMT. On the right, you see, again, a chart, which is used to obtain two independent informations. The first one is the classification of the soil. So you come in with the x-axis, the material index ID, on the y-axis, the ED, and you land on a point, for example, here, which is silty clay or clay silt or sandy silt, according to the color or mud. And the second independent information is the number in this box, which represents the unit weight of the soil as a ratio to the unit weight of water. This is used, the unit weight, to construct an approximate profile of the vertical stress, which is used in the processing. If there is valuable and very accurate independent soil, generally laboratory results on the unit weight, it can be input directly in the software to override this classification, which, however, works really, really well, and 95% or even more the processing is done with this table published by Krabs and Marchetti. Now let's look at the intermediate parameters. So if we do a DMT test, we will immediately notice that the two pressure readings, P0 and P1, which are A and B corrected, have a ratio about 1.1 to 1.3. Whereas in sand, the second pressure reading is at least 2.5 times the first reading. So while you do the measurement, you already know if you are in clay and sand according to this ratio. And the silt, of course, is somewhere in between. Now, the definition of ID is somehow related to this difference, P1 minus P0 normalized in a certain way. And just to give you an idea, we needed to use a logarithmic scale due to the high variations, which is good, to distinguish between the clays and the sands. So you see in the sandy layers, readings like 2.61 and 11.90 with a ratio of about 4 to 5. Whereas in the clay below, the ratio is about 1.1, 1.2. The second and most important DMT parameter is KD, which contains information on stress history. KD is defined as P0 minus U0 divided by the effective vertical stress. The formula is very, very similar to K0, where P0 minus U0 is the horizontal effective stress. Well, unfortunately, KD is not K0 because the blade had to penetrate the soil, incrementing the horizontal stress and somehow a little bit disturbing the soil, even though applying the minimum disturbance possible compared to any other tool you may think of. So KD has been defined as an amplified K0 because P0 minus U0 is an amplified version of the effective horizontal stress due to the penetration of the blade into the soil. However, I will show you that in clay, KD is very, very well correlated to K0 and to OCR, providing good estimations of these parameters. Now, KD can be read in this way. If we are in a normally consolidated clay, the value of KD is not generically small. KD is equal to 2, whereas as the soil is over-consolidated, the value is higher. according to the amount of overconsolidation, or also cementation or structure, or any other phenomenon that increases the performance of the soil. Now, this is an example of a test site performed by Professor Marchetti in the last 80s. I had barely 10 years old. And you see in the top 10, 14 meters, it's basically KD very close to 2, indicating silt, sand, and clay material. But then at 14 meters, you can detect a very overconsolidated clay or silty clay below, which was confirmed also by laboratory tests. For what concerns OCR, the formula was provided with experimental results from Marchetti, who went in many research sites that were very well documented and where the OCR value was approximately known. And it's nice to show that 15 years later, in 1995, Kamei and Iwasaki published a paper where they added a lot of many other points, experimental and theoretical points, and showed that the curve presented by Marchetti 15 years before was very close to the best fitting curve of also these additional points. There are also theoretical publications showing that this formula is well conditioned and well based, also from a theoretical point of view, and again showing very good agreement with the validation and experimental points. Similar process was used for the estimation of K0 from KD for the horizontal stress. Again, here the experimental points lie very well on the curve, perhaps with even less scatter than for OCR. You see very, very consistently. And again, in the same work of Yu in 2004, you can find again a confirmation from the theoretical point of view of this formula of K0 as a function of KT. Just to show you an example where the K0 parameter was employed successfully, here we are in the south of Italy, where there was a terrible landslide very close to a railway. And the engineers decided to do a test very close to the landslide, a little bit farther away, and then very far away as a reference for the horizontal stress. And as you see in the graphs, the three profiles show very well the decay of the horizontal stress going closer to the landslide. And of course, this is an application of using K0 with the vertical stress to obtain the effective horizontal stress in clay. Now, the third intermediate parameter is defined as the elastic modulus of the horizontal load test performed by the membrane expansion. So if we accept some elastic conditions that you may read in this publication of Gravison and perform some calculation, it is very simple to obtain ED equals 34.7 times the difference P1 minus P0. ED is not a modulus to use directly for many reasons, among which the fact that the soil has been penetrated by the blade, and so the modulus is not the modulus before penetration, so it requires some correction. However, it is a direct measurement of a modulus and not an inferred modulus. Only the dilatometer and the pressure meter measure in situ the modulus directly. Now, to obtain a usable modulus, Professor Marchetti decided to correlate to the constraint modulus. Why? Because it was the easiest target to obtain using laboratory results in well-documented test sites in order to obtain a very valid correlation. In fact, the modulus ED is corrected according to the soil type that we have thanks to ID, if in clay, silt, or sand, and according to the stress history parameter KD, where we know if it was normally consolidated or over-consolidated. So these three ingredients are used in the formulae that came out from the correlations to provide their contribution of soil information to obtain a valuable estimate of the constraint modulus M, which is the vertical trained confined tangent modulus at the effective vertical stress at the current depth. There are many comparisons of and publications of comparisons of the modulus obtained from the DMT and from laboratory tests like Dilutometer or other tests showing excellent agreement. I reported here 3 examples in 3 continents: USA, Norway, where you see that the odometer perhaps has some additional scatter compared to the dilatometer profiles, 2 of them, and the shaded area is the area between the 2 profiles. And also in Japan, with the Tokyo Bay clay, you see a very good agreement with the odometer parameters. For what concerns the strength in the clay, the way in which the DMT provides SU is to use the chance relation, very much promoted by Professor Ladd, saying that the ratio between SU and the effective vertical stress in a soil is equal to the same ratio in a normally consolidated soil times OCR to the power of m. Now we know that OCR may be estimated with KD in clay with this expression, and the exponent m may be estimated with 0.8 as suggested by Ladd himself, and the ratio SU over effective vertical stress in many soils is about 0.22 or 0.23. So if we combine all these expressions, we obtain a closed formula as a function of KD and effective vertical stress to estimate SU. Again, you may find several publications that are now well old because they are consolidated in terms of reliability. But let me propose you these ones from Brazil, Canada, and Japan, showing very good agreement between the ones obtained from DMT and pressure meters and triaxial test and CPT, showing with the thick black line that pass right through all these points. Same in comparison with the field vane test, which are the black points, and the black line is the DMT, showing again a good agreement in this site of Canada. And in the same site of Japan in Tokyo, again, you see the profile of SU from the DMT passing right straightly through the triaxial test. This is the research test site in Italy, where you see again a publication from the National Society, Italian Society of Geotechnics, where many tests were performed, laboratory and the field vane test, and the DMT, which was in excellent agreement, and also the CPT. Although with the CPT, you know, there is that NKT or NC factor that may vary from 14 in this case to 22. And this may change the profile according to the value that you have to input somehow. But fortunately, in this case, there was information that allowed to calibrate this parameter. With the DMT, as we saw, fortunately, the formula is closed, function just of KD and effective vertical stress. Let me introduce you the meaning of the C reading, which is the closing pressure after the deflation of the expansion of the membrane. This publication was first introduced, this concept from Schmerber in 1988, showing that in sands, the C reading corrected to P2 with the calibration of the membrane provides exactly the water pressure. In this site, the sand layer, both at the top and at the bottom, provided that the points of the P2 were on the hydrostatic line. Whereas in clay, they highlighted the excesses of the water pressure due to the penetration of the blade. So an additional intermediate parameter called UD was defined as the distance between the point and the water pressure. And when P2 is equal to U0, UD is equal to 0, indicating sand, or anyway, drain material, or geomaterial. Whereas when the pressure is different, generally higher, then we are in clay. And when we approximate and get closer to the sand, you see how gently the C readings go and then lie again on the sand. So really, indeed, UD is a valuable parameter to distinguish between drained and undrained layers. This is an example of a test site in a silty sand or sandy silt, where the interest was to determine if it was a drained or undrained behavior for the design, and the C readings enabled to show that they were lying all on the hydrostatic line, indicating that UD was basically 0, exhibiting a fully drained behavior of the soil. An additional measurement that can be performed or test procedure is the dissipation test. This is generally done in cohesive soils, clays or silty clays or silts and even silty sands, now that we have the Medusa. And the test consists in advancing the blade and stopping at a specific depth. And the extra pressure created in the cohesive soils by the penetration of the blade will start to dissipate. The time t equals 0 is taken when the penetration stops at the depth of the dissipation. Only the A reading is repeated. And with the traditional DMT, you just have to reach A and deflate without any membrane expansion, or else we will cause an additional dissipation due to the expansion of the membrane. So we take the A reading with time, and we start to double the time with the manual traditional DMT. And then we plot the curve in a semi-logarithmic space, showing the time on the x-axis and the A reading, or the total horizontal stress, on the y-axis. Excuse me. Now, the flex point of the S-wave curve that is generally obtained provides an indication on the coefficient of consolidation using this formula that you can read in the publication of Tolton et al. And from that, you can go to the permeability coefficient, KH. Of course, the dissipation test can be done also using the cone, where you, however, are taking the water pressure from a singular, highly disturbed point, where not always it is easy to saturate with a silicone oil or some other jelly substance. And especially it is related only to a singular point in a highly disturbed area. With the wedge shape of the DMT, first of all, the involvement is of a larger volume because the membrane is larger, sort of like a mini embankment. And also, the soil is much less disturbed, preserving the original state of the soil and therefore its dissipation behavior. The validation of this consolidation coefficient was first done in 1998 by, again, in this publication, you may find the details, and it compared very well with the laboratory results and with the back analysis in a real case project, and more details are available in this paper. Today, with the Medusa, it is possible to obtain very rapid A readings automatically with going down to 0.01 minutes. So even the initial part of the dissipation is very well captured compared to when you do it manually, where you sort of miss the first part due to the unfeasibility of very rapid A readings. Whereas the automation can maintain the membrane basically and virtually in equilibrium, obtaining these first points. And as you see, the curve is very well and harmonically S-shaped, defining a good flex point. This test was done in Hungary in October 2020 using the automated dilatometer. Now, the DMT is already coded in the European standard, Eurocode 7, in the ISO standards recently, and ASTM since the year 2000. This is just, these years are the latest publications and renewals of the standards. And this document is not a standard, but it's a document written by the International Society of Soil Mechanics and Geotechnical Engineering, a technical committee named TC16, and today it's named TC102. This document contains the most important details on the equipment, on the test procedures, and on the processing, and even some applications that we don't have the time to see in this presentation. There are also several national standards: Italy, Sweden, France, China, and perhaps some others that we do not know of. The DMT instrument is used in over 80 countries. Each red point corresponds to an equipment. There are about over 600 in the world, and they have been used also in areas that have no red points, especially in Africa, where European companies or the South African or the Egypt companies go to do the test. But the concentration is mainly in North America, Europe, and Eastern Asia, but it has been strongly increasing in South America, Australia, and New Zealand in the last 5 years, and we have to update this map considerably. Now, what are the main differences between a CPT and a DMT? Now, the first one is the flexibility in penetration methods. We already said that the CPT requires to, and you have seen yesterday, to make the measurements by advancing at a fixed penetration rate of 2 centimeters per second. This means that you necessarily need a penetrometer to push at this constant rate and to record the speed of penetration to ensure it is correct within certain ranges. The penetration may affect and influence the results, especially when there are interbedded layers of hard and soft material which vary the velocity, and it is very difficult to ensure a constant speed. With the DMT, there is no specific requirement on the penetration rate, and there's high flexibility because the measurements are performed when the blade is not moving. So you can use a penetrometer, a drill rig, a floating barge, dynamic, and many other solutions because the measurements are independent of the penetration rate. We have already seen this picture, but it is important to underline that the penetration of the blade causes less distortion compared to the penetration of conical shaped probes like SPT and CPT, where the soil is brought to failure and therefore loses its original state. And then the soil parameters with a blade are more representative because they are in a less disturbed area and provide less uncertainty. This is useful because then in the design, it may allow to use less conservatism on the coefficient of security. Another important difference with the CPT is the sensitivity to horizontal stress. The arching effect is very well known when we use it in tunneling, for example. In this case, it is a negative effect for circular probes because when circular probes penetrate, they create a very stiff pre-stressed cylinder, which is like a barrier to the horizontal stress. And therefore, it is insensitive to this horizontal stress, especially when it is the aim of a design, like for quality or soil improvement projects. With the blade, the relation between and the ratio between the width and the thickness of the blade is such that the arching is very, very negligible. And moreover, the measurement is performed in the horizontal direction, sensing very well the increases or decreases of the horizontal strength with depth. Let me show you this experiment performed by a research group in Korea by Lee et al. In 2011. You can read this publication. They recomposed specimens of sand at different relative density values, about 40%, 60%, and 80%, and distinguished between normally consolidated sand and over-consolidated sand. They then performed both the DMT and CPT tests. And with QC, they were able to very well distinguish the relative density. QC is well related to relative density, as you see in this curve, but is completely insensitive to distinguish between normally consolidated points and over-consolidated points. With the DMT, and in particular the KD parameter, the stress history index or stress index, the same specimens showed that they aligned very well on parallel curves increasing with OCR, showing that KD is particularly sensitive to OCR increments and therefore to stress history. With the dilatometer as well as the pressure meter are the tools, as I said previously, that measure directly the modulus of the soil. Everyone knows the difference between stiffness and strength. And in this very qualitative graph, we have the same 3 different soils with the same strength, but different stiffnesses. And when you measure only the strength, you then have to somehow guess the stiffness with coefficients that vary apparently significantly between 3 and 27. This is shown also in this graph, which is the degradation of the soil modulus with strain. And as you see, the flat dilatometer is located right in the range for deformation analysis, indicating that this modulus is already in the right range for deformation calculations. With the SPT and CPT, you are measuring at very high strains, and then you need a factor to obtain the point in the range for deformation analysis. However, this factor is very variable, providing some difficulty in absence of independent knowledge with other testing or other independent information. Now, the main applications for which the DMT is used are shown in this slide. We don't have time to look into all of them, so let me just show you the settlement prediction. We all know the well-known formula of Terzaghi, where we need the increments of the vertical stress due to the load obtainable with Businesq, or using the modulus M obtained from the DMT. Of course, there are formulas that are more complex with additional parameters, but especially Professor Marchetti was a fond supporter of this simple formula, where a good estimation of the modulus M would provide a very valuable settlement, which is better than having a very long and complex formula and then make a mistake of an order of magnitude of the modulus, and therefore also on the settlement. So you may find many publications and case histories a very good agreement between measured and DMT predicted settlements or modulus. Each one of these is an example. Let me show you a few. This is a very, very recent paper that will be published by Roger Feil-Metzger in 2020 at the Conference of Budapest. And he reported 107 projects showing that the dilatometer saved the owner significant money over the previously overly conservative design based on less accurate tests. So each name is the name of the project and the money that was saved with the foundation, the redesign of the foundation. The projects are 107, and the total cost of the savings were over $21 million. This is another publication by Godleski with a who recovered 28 buildings in different soil types, showing that the settlement obtained from DMT estimates was in very good agreement with the measured, and all these buildings were structures with shallow foundations, but in different soil types. This is another example of settlements on a very poorly designed foundation of a mat under these silos. The measured settlement was over 60 centimeters, as well as the DMT prediction with an over prediction of 22%, which is acceptable. And also the modulus was back calculated thanks to the measurements of the deformations with depth. And you see the red points are the measured modulus, back calculated modulus, and the blue is the DMT profile, showing a very good agreement of the modulus M. Now let me show you an example of SDMT test and an evaluation of the settlement, as you may do it in any project. So when we were doing a workshop in Colombia, me and Professor Robertson, again in Bogota in 2015, in about 3-4 hours time of the workshop, they did a 30-meter test outside with a drill rig, as you can see in the picture. In this clay, the material index showed very well that it was a clay with a very top crust that you can see behaved more like a clay silt or silt at the very top because it was desiccated and with a higher performance. You can immediately see that from the KD parameter, the value of 2, normally consolidated, and that top crust, which is also quite deep compared to other crusts around the world, up to 6, 8, or even 10 meters before KD gets to the value of 2. The modulus M, so the constrained geometric modulus, the undrained shear strength with the formula I showed you previously, and the shear wave velocity with the seismic measurements. Using the formula I showed you before for OCR, you see very well that they fit perfectly what is expected. OCR equals to 1 in the normally consolidated layer below 10 meters, and very high values, even above the expected, in the top desiccated crust. And again, K0 with the formula obtained K0 of 0.5 in this place, in this clay, in the layer between 10 and 30 meters, which is a perfectly expectable value in a normally consolidated clay, with much higher values at the top crust, perhaps even too high for what is possible, but it well shows the higher performance in these top layers. Now, for academic reasons, we did also an example of a settlement prediction with a rectangular load of 15 times 30 meters with 30 kPa, just to simulate a settlement. For the information of the soil, we uploaded the UNI files, which basically provide the modulus with depth every 20 centimeters from the DMT. And immediately we had the settlement evaluation with the monodimensional formula of Terzaghi for the settlement, with a quite high settlement in the center, in the four corners, and in the median side of the two sides. And just to show you a profile below the center, you see the modulus that we already saw in the stratigraphic profiles. The modulus is high in the top crust, and then exhibits a minimum at the normal consolidated clay, and then it increases gradually with depth. The vertical stress increment, of course, decreases with depth, and the strain has its maximum as soon as the crust is over, so around 6-8 meters, where the load is still high, and then, of course, it decreases because the modulus gradually increases, but especially the load obtained from Boussingacs decreases with depth, the increment of load. So this is just to show you how simple it is, even on site, to do a rapid evaluation, just a qualitative evaluation of the settlement, directly using this software, which is even a freeware that you can download. The DMT is commonly employed also in quality assessment of soil improvement, ground reinforcement, ground improvement, and ground treatment. One of the first publications on this topic was in 1994 by Professor Vainipe in New Delhi. He showed the experience in Belgium in a loose sandfill compacted with vibrocompaction techniques. He performed a DMT test and compared KD before the treatment, with its which is the dotted line, and after the treatment, which is the continuous line. The KD parameter increased 4 times, whereas the modulus M increased 10 times, showing that the compaction was efficient, and also showing that below 8 meters, the value was then the same, indicating that the treatment was valid and efficient up to 8 meters. Another example in the USA, North Carolina, was this project where the compaction method was a resin injections in sands. And as you see again, the pre-treatment and post-treatment showed showed very well how the improvement was efficient with this technique. A third example I want to show you is for the Palma Island in Dubai. Most of you may know that this island is artificial, obtained with the dredging of sand from the sea floor. It is then compacted with vibrators and heavy machines to compact the soil. And the interest here was to confirm the overconsolidation obtained with the vibrocompaction detected by VS. And they did the CPT and the DMT only after compaction. And this is the profile of the CPT, and this is from the DMT, showing that the DMT is more sensitive in the variations. However, the authors conclude that the ratio M over QT is the most reliable way to detect the well-compacted areas from the less compacted areas, where the value of 10 is a good threshold to detect the two. So if you want more details on this, you may read this publication of Sharif. So to summarize, for the quality assessment of soil improvement using the DMT, it is recommended to perform the test, both DMT and SDMT, before and after the treatment, and then compare the profiles of KD, M, and VS. Sometimes it is not possible to perform the test before the treatment, but only after. In this case, it is recommended to perform both DMT and CPT, and then examine the ratio M over QT and check that it is higher than 10 or 12. Finally, the last application I want to show you, because we're running out of time, is the DMT K equals 2 method to show the landslide, but I have to skip this because I don't have time. I'm sorry. Let's go to the Medusa DMT, which is the automated dilatometer. It is composed of a set of batteries, an electronic board, and a motorized syringe composed of an electric engine, a piston, and a cylinder. There's a pressure transducer to record the pressure values and a blade with standard dimensions. The equipment is very, very compact because it doesn't require a gas tank, a control unit, and the pneumatic cable. And the equipment is very compact also to transport. Only the blade and the rod are a bit long, but they can be carried in golf suitcases. The pneumatic, a comparison between pneumatic DMT and Medusa DMT is the following. When performing the standard pneumatic DMT, the operator should inflate the gas to obtain both A and B readings in about 15 seconds, with plus or minus 5 seconds in the Eurocode, which is not really simple unless the operator is somewhat trained or skilled. All the DMT tests were performed with traditional DMT, so it is not really an issue. But in really soft soils, it may happen that going off of these standards may provide problems. So the Medusa DMT is automated for this. So its hydraulic is able to obtain A and B exactly in 15 seconds or plus or minus 1 second with a very high repeatability and benefits in increasing the accuracy. This is a test cycle of the Medusa DMT. You see that the piston, this is the piston position, the current of the engine, the contact of the membrane, and the pressure. As the piston advances in the syringe, the pressure increases, and when the contact of the membrane goes off, the A reading is taken. Then the speed is increased to obtain the 15 seconds. For B, you see 15 seconds after A, and then its contact goes on, the B reading is taken, and then slowly deflating to obtain C. Now, the Medusa DMT was first validated in the Zlasting Most tailings dam in Poland, which is the second largest world's tailings dam, obtained from the waste of a copper mine. It is now over 66 meters. And we validated the Medusa DMT with a heavy truck penetrometer in the cold month of 2019. And you see that the aim there was to distinguish between the top compacted areas with the modulus and the lower uncompacted zone below 6 meters. So this was the first validation. And several tests were performed in this with the Medusa between 2019 and today. Now, let me show you the last topic I want to show you because it's important and very actual today. In sands, the A and B are fully drained. In the clays, the A and B readings are fully undrained. In most silts, A and B are partially drained, and the correlations of the values are all adequate and okay for the soil parameters. However, Professor Marchetti indicated a small family of silts defined as niche silts where A and B are partially drained to a different extent, to the point that the difference B minus A is too low, and so are ID and ED too low, which because they are a function of B minus A, with the fact that MDMT is underestimated as a function of ED and ID. This can be very well seen by this graph, where during the test, starting from time 0 when penetration starts and monitoring the total horizontal pressure, the A reading is 15 seconds and B seconds and is fully undrained in clay, whereas in sand, the behavior is so rapidly to drain that by the time you take A and B, they're both drained. The problem is in the niche silts, where the A reading is slightly drained and the B reading is heavily partially drained. So the difference B minus A is inconsistent or too low. So the DMT may detect this partial drainage with short dissipation tests in the first 15 seconds. If there is no appreciable drainage, you simply continue to do the standard test by taking the last reading at 15 seconds and then go to B. If there is appreciable drainage, you then wait 1 and 2 minutes for the dissipation to take place, and then you expand to B. If you're more interested in these details, you can read the publications of Schneid between years 2019 and 2020. So last, these are 2 examples of a negligible partial drainage. Here we are in a clay This test site will be published by Monaco at the conference in Sydney. So you see that the repeated A readings in the first 15 seconds have a very low decrease of the A reading, and then you simply go to B and C. And the last A reading with B and C are equivalent to a standard DMT test. Here, in this test in Brazil, the Medusa was taking many A readings that decreased with depth, and significantly, because there was partial drainage. And only after 100 seconds, we then increased to take B and C reading. So if we plot that dissipation curve I just showed you in a better scale, you see that the decrease is very high, from about 450 to 330. So over 30%. And if we plot it in a log scale, we even see a flex point to estimate CH and KH, indicating very high partial drainage. So I inserted this topic to give you an idea of additional tests you can perform with the Medusa. And finally, this is an additional test procedure, extremely new, that you can do with the Medusa. Basically, to do the test like the CPT, you penetrate with the membrane in equilibrium with in the A position, like when you do a dissipation, but you penetrate the soil. Basically, you're measuring the total horizontal stress with depth, and it is perfectly undrained because there is no time to dissipate, even in partially drained soils. Then the A readings are plotted with depth, and the B reading may be taken, for example, every 1 meter when you change a rod. So preliminary tests that will be published in the paper in Budapest have shown that this procedure, the green plot, evidenced and showed a good agreement with the standard DMT test that showed a change of layer between 7 and 9 meters, captured also by the this other procedure. And this is the an additional 30-meter test just using this DMT while penetrating and with B readings taken every 1 meter. I can't show you additional results on this because they will be published in the proceedings of CE. I apologize for the delay of a few minutes. This is my email. If you have questions that you may not pose in this during this session, you can find additional documentation at this website. It is a bibliographic website with many papers, most of which I've referenced in this lecture. And if you're interested to know the latest updates, latest measurements, we perform also with research and also test sites around the world. You can follow us on LinkedIn at this contact. Thank you for your attention.
Okay, let's take the first question. I think there are 2 questions. So the first question is, what is the distance between 2 sensors of SDMT? And the second question is, how does DMT compares with PMT, pressure meter test?
Okay. For the first question, yes, the sensors are spaced half a meter because we found it optimal when we did our researchers. If you do less, it's too inefficient to do the test and too expensive to do the test every, for example, 20, 30, or 40 centimeters, and 50 looks like a good optimum. If you do more than half a meter, perhaps in very homogeneous soil, it can be an option, but in heterogeneous soil, you may miss a valid resolution to distinguish between meters of half a layer in 1 meter. And not only this, but also the wave can be very different, too different in 1 meter. And when you go to evaluate the delay, the shape of the wave can be different, and the delay can be difficult to evaluate, and you can be inaccurate. So that is why we came up with 0.50 centimeters distance. If the soil is very homogeneous and you want to save the time, you can simply do it every meter because you know it's homogeneous. And so you do an average measurement in half a meter and you skip a half a meter. I know clients who do this when they are sure that the soil is homogeneous. For what concerns the pressure meter, there are several comparisons that I also showed you in this presentation, showing very good agreement of the modulus M, where in very well documented research test sites. The pressure meter is an excellent choice, especially in soils that are not penetrable, where the DMT cannot be performed. So you can drill a hole and then put the pressure meter inside and measure the modulus directly, like the DMT. It's probably the best solution. In a softer material, the DMT can be a more simple solution because you may drill a hole and not have a problem of having a calibrated hole and a very expert driller that makes a good hole and an expert user of the pressure meter for performing the test. But the quality of the pressure meter tests are really excellent and compare well with the DMT.
Well, let's take the next question. So is there a direct correlation between the ED and ES, the elasticity modulus?
Yes, actually, Professor Marchetti preferred to go from M, the modulus M DMT to ES. The reason is that ED is a modulus that does not take into account stress history. The correction of ED with not only ID, but KD is important to provide a valuable modulus M, because there is the information of the horizontal stress, which is important for settlements and for a reliable modulus. So to answer the question, the relation is between M and ES, and there is a formula published by Main. I think I have it somewhere in my computer. So if the person doing the question sends me an email, I can send him this way of going from M to ES.
The next question is from Ali Reza, and he refers to the case of the Toronto project chat. And how is it possible to have a normally consolidated clay above over-consolidated clay?
The answer is that at top it's very common to have a over-consolidated crust. So if he's referring to the Columbia, not to the Toronto, but to the Columbia test in Bogota, it is very common at surface to have over-consolidated layers that are not maybe over-consolidated from history, but they may be essiccated crusts or cementation or some other type of higher performance of the soil due to any possible reason. The KD and the parameter of stress history detects the performance of the soil. And if you get a very extremely high pressure, there is because the soil is resisting when it is not resisting when you're deeper and you obtain KD equals to 2. So it's a performance-based test behavior, and you then may try to find the explanation, but the performance is there and is measured.
Yeah, no, I think that's also the experience with the tailings, that we see a top crust because of desiccation, and that kind of leads to an over-consolidated kind of a behavior. So this is about the coefficient of consolidation. So usually the coefficient of consolidation is obtained in the horizontal direction CH. So how do you correlate that to CV, the vertical coefficient?
Well, the point is that the coefficient of consolidation in the horizontal direction is taken at various depths, and you construct an approximate profile. In the single point at the horizontal direction is the same as the vertical in that singular point, because the dissipation occurs in all directions in front of the membrane. So when there is a difference with depth, we simply do several dissipation tests at different depths, and then we make an approximate profile.
And how do you convert that to vertical? Is there a way to convert it to vertical coefficient?
No. No, I don't know how the designers then use the coefficient of horizontal stress, but when they need to do it vertical, they do it many times at many different depths, and then they use it this way.
Yep. Okay. Can you share some of your experience in conducting DMT in residual or volcanic soils? Are there any unique characteristics in terms of DMT readings, KD, ID, and so on?
There are several papers concerning residual soils. Volcanic, yes, we have some results also there, but again, particular characteristics in terms of results. They're not going to change because you are in a volcanic soil or in a residual soil. You will get the parameters. I recall that in a residual soil in Brazil, they proposed some slightly modified formula for some parameters. And but for the rest, in all the experiences, there is no particular recommendation to do the measurements differently or to check for something that has to be changed in the procedure or in the processing of the results.
The next few questions are about the Medusa DMT. So people are asking, so it does not have any cables or monitoring unit. Is it just a probe equipped with a data acquisition system? And finally, how does the price of Medusa compare to the pneumatic DMT?
The Medusa DMT was designed to work without a cable. However, it's not recommended unless it's really necessary, because you want to see the results real time. Whereas if you don't use the cable, it only saves the A, B, and C readings. So for deep offshore below 2,000 meters, you may want to use it of water. You may want to use basically without the cable. But now, for example, in October, we're going to do tests at 1,500 meters of water, and we're going to use the cable of the seafloor pushing system where the data will pass. And so you can use an electric cable just like the CPT, which is purely electric and not pneumatic anymore. And this way you can see the results real time and change the measurements you want to do. Whereas when you have no cable, you have to pre-program the measurements you want to do with time, and then you have to follow that scheduling of time because you have no way to communicate with the Medusa. So I hope this answers the question. The Medusa is more expensive because all the top surface parts, basically the control unit, and also part of the electronics and a part of the software in the computer is basically inside the Medusa DMT. You're bringing down parts that were up, including a part of the operator who did the test. So it took us 6 years to develop it completely, more 7 years, and to make it work with reliability and distribute it. And also another thing is that when you if you accidentally broke the rod, you lose the Medusa DMT. So it's much more expensive than changing just a blade. So it's approximately, a system of the Medusa is approximately the double of the system DMT, but the blade is much more expensive because it includes everything else behind it.
I think I agree with you there that when people are talking about cost, they should also be taking into account the operator cost, the data analysis cost, and in case of Medusa, a lot of it is combined as well. So that definitely offers some advantage in there, the way I see it.
Yeah, that's a good point. Yeah, you save. You have also savings in terms of the person you send on the field. Definitely, yes.
There are two interesting questions, and this is relating to the always had debate about CPT and DMT. What are the comparison? What are the advantage and disadvantage? And then can you comment if we can increase the efficiency by combining CPT to DMT?
Yes, well, the CPT is definitely a valuable instrument, and especially for qualitative testing. There are many, especially in Holland, where it was born, the interest many times was just to see at what depth was the hard material to do the piles. So they pushed the CPT, and when they found refusal, they knew the depth for using the piles. But if you want a more sophisticated diagnosis or basically analysis of the soil, the DMT may be a valuable choice independently or even in combination with the CPT. I tried in this presentation to show you how the DMT has two specific important additions to the CPT. The stress history, due to the sensitivity to the horizontal stress, which the CPT is basically unable to measure, even with the friction sleeve, for the arching effect that I tried to explain with some slides. And the second point is the modulus. With the modulus, if you are measuring a modulus directly, ED, yes, it's true, you have to do a small correction, but you are starting from a modulus, and you will obtain a modulus with a small correction. So if you need reliability in terms of modulus and stress history, because they can be important in your project, and you don't want to be too over conservative, like with the SBT and somehow even with the CPT, because of this insensitivity to horizontal stress and modulus, then the DMT may be a better choice. So it is a little bit more expensive in terms of time, because you have to stop and perform the measurement, but you get much more information. So very commonly in a big test campaign, they do perhaps some CPTs and then also DMTs, and maybe they calibrate the CPT with the DMT because it's faster. And if they have to do thousands, they can do have a calibration between CPT and DMT in that specific site. Now that the DMT can be advanced with the while penetrating mechanism with the medusa, it will be as fast as the CPT. So I believe that even this disadvantage compared to the CPT will be removed. But we need still a little bit more time because it's an experimental procedure we are starting to test.
And do you see these two techniques being combined at one stage in future, a combined probe that can measure CPT and DMT?
No, I think it's impossible, because you cannot put a CPT and a blade in the same vertical profile. If you use the CPT, it's a circular shaped probe, and while the blade is flat. So you cannot do it in the same test.
That's all good. Amir asks a question about how much can we rely on the OCR, the over-consolidation ratio obtained by DMT in shallow depth, essentially in the top crust layers?
No, in the top crust layer, really, my answer is that you can rely on it, but indeed the soil somehow is extremely compacted, maybe in the 20-40 centimeters, and the values are very high, because when you relate the horizontal stress, it can be extremely high, while the vertical is very low because you're at shallow depth. So you really get high values sometimes, and I would consider it more qualitative, because these high values cannot be used, I think, in design. But they definitely tell the designer that at that top crust you can load it a lot. Generally, it's not thick, so it's a spike, or it's a high value that lasts for 1 meter, most cases are 2, and then the OCR is reliable in clays. For what concerns OCR, the DMT OCR in sands, OCR is sensitive to variations of OCR, but there's no unique correlation as in clay. So if in clay you can obtain directly OCR from the DMT and from KD, in sands you see only the variations, but you need to do a first calibration to obtain OCR.
There has been also some interest about the Medusa DMT. So how from Shenzhen, China says that he found it interesting on the continuous A reading measurements from the Medusa DMT. So basically it can also be used as a geotechnical monitoring device rather than just a site characterization tool. For example, for the purposes of monitoring stress changes during excavation or tunneling. How about the battery life?
Yes, this is a correct evaluation. The battery life, well, if we have a cable, we normally, like I always did test with the cable at the moment, except in laboratory where we are testing also the cableless. But with the cable, you continue to charge the Medusa while it works. So many times we left overnight the system to continue the dissipation, because in clays the dissipation can take more than 1 day. So it is possible with a battery that continues to power the system, a normal car battery. There's not much energy involved. If you want to do it cableless, there is a limitation, of course, because the battery inside I think it can work according to the pressure. It should be guaranteed for, should be able to work for 1 day, 24 hours, or if the soil is not extremely hard, even 36 hours.
Okay.
But you can increase the battery if you really want to. You can just add a battery pack behind it, and you can make it last additionally if you really want to, when there is no cable.
The next question is around what is the reliability, what is the lower limit of reliability on soft soils for DMT measurements in terms of strength?
Okay, very nice question. I am presenting with Professor Danziger from Rio de Janeiro a paper to ISC 6 in Budapest, a paper on this. They have a test site there, which is nearly liquid soil, 20 centimeters of water, and then a very, very, very extremely soft clay. And they did a test with the traditional pneumatic DMT and published that the results had too much scatter in their opinion, because if P0 and P1 were extremely repeatable, their difference, P1 minus P0, that was of the order of 5-10 kPa, which is really, really nothing, then they said that they experienced unreliability with the standard DMT. So with the Medusa, I went to do the test there, and the repeatability improved a lot, not only of P0 and P1, but also of the difference, P1 minus P0. So with the Medusa, you have a big advantage in extremely soft material, and also offshore, of course, in at large depth of water in the first meters, where the soil is typically very, very soft. With the pneumatic, you are limited to the flow of gas and to the length of the cable, which has a capacity. And therefore, in extremely soft material, even a small variation of pressure at the opposite ends of the cable can give some scatter, even though an attentive and expert DMT user may do so even with a pneumatic equipment.
This question also came for CPT. If there is any plans around developing DMT tool with imaging capability.
Anyway, the image processing, you said to put a camera in the probe is the question.
Yep.
I thought many times of this, but I'm not really informed of how valid this approach is. So if the person doing the question thinks it's very useful and has some documentation and sends it to me, we would be happy to try to think of it and perhaps experiment it with him. It's not so simple to continuously add the sensors, but today cameras are very small, so maybe it is possible. At the moment, the answer is no. We don't have it, and we are not planning in the near future. But perhaps sometime in the future, yes.